Hello, everyone. Welcome to this episode of the Galaxies Science Interest Group seminar. Today we have Harley Katz coming to talk to us about the extreme nature of galaxies and stellar population at cosmic dawn. So Harley was an undergrad at the University of Maryland, College Park, very close to where I am now, and then did his PhD in Cambridge. After that, let me see if I get this right. He became a Beecroft Fellow at Oxford, also in the UK. And then somewhere in between, he co-founded a company, which I don't think he's going to talk about today, but a very interesting story that I heard on another day. So it's also not an astrophysics thing, right? It's a biomedical thing. And then was
Genetics, yeah.
and it became Forbes on 30 under 30. And then here he is now as a faculty member at the University of Chicago. So I don't think I missed anything. But Harley, we're grateful to have you here to tell us about your latest research. So take it away.
Yeah, thanks, Aaron, and thanks also to Bene for having me here. It's great to talk to you all about high redshift galaxy formation, which is a topic I've been thinking about for well over a decade now. I'm primarily a theorist based at University of Chicago, mainly interested in high redshift galaxy formation simulations. But obviously, like the rest of us, I got extremely excited about the observations as well. So while the sims have been running for the past 2 years, that I'm finally excited to be able to show you, I started dabbling in the observations. So the way this talk is going to go is I'll talk a little bit about sort of where we were before JWST, where the simulations are now, and then what I'm excited about moving forward, especially places where the simulations and observations are in disagreement. So with that, I don't think you can talk about high redshift galaxy formation without showing a slide like this. It's more or less the history of our universe on a single slide. On the left-hand side, we have the Big Bang. About redshift of 1,000 was when the CMB formed. Okay, the universe was hot, it was expanding, and as it expanded, it was cooling down. Okay, and about 100 to 150 million years after the Big Bang, gravity really started to take hold, and we started to see these first sources, which were metal-free population 3 stars. Okay, and we think these sources were very hot. In some models, they were very massive. They emitted copious amounts of ionizing photons, which started to carve these H2 bubbles. As the metals from these population 3 stars polluted the interstellar medium and intergalactic medium, larger galaxies started to form because cooling was much more efficient. Gravity was pulling more matter in. And by redshift 6 or so, now actually closer to redshift 5.3 is our best estimate, reionization was completed. Afterwards, the universe sort of evolved for another 13 billion years until the present day. Okay. And sort of with Hubble, we were able to push back to around a redshift 10 or 11. Those were our best constraints. The highest redshift spectroscopically confirmed galaxy was about a redshift of 10.7. Okay, and then the promise of JWST is, especially if we're lucky, we can go at a much higher redshift and maybe even get back to cosmic dawn, the formation of the first population 3 stars. So pre-JWST, you can ask what the status quo was. From an observational perspective, Hubble was providing us mostly the galaxy number counts at high redshift, UV luminosity functions, photometry, galaxy sizes, things like that. If we wanted probes of the interstellar medium at cosmic dawn, we were primarily relying on ALMA for single line detections like oxygen 3 or carbon 2. For intergalactic medium studies, we were mainly using things like quasar sightlines, things like Lyman alpha as well. And then finally, if we were very lucky for exceptionally bright sources, we could do ground-based spectroscopic follow-up with instruments like Mossfire and X-Shooter. And as a theorist, I would say in the pre-JWST era, life was pretty good. I mean, there's just two examples of two simulations. On the left is Thesan, on the right is Sphinx 20. And you can see that as a function of redshift, you're looking at UV luminosity functions. And pretty much every simulation was not having a problem matching the UV luminosity functions at high redshift. And this is primarily due to the fact that this observation is not highly constraining, but also with limited data, especially at the very highest redshifts where we know there's sort of more of a tension now. It wasn't too hard to get things right. Similar was the case for the interstellar medium. Here you're just looking at ionization parameter on the y-axis versus metallicity. The colored points are just constraints from above redshift 3. And on the colored points, purple and blue are from simulations. And again, there's really not that much data, so you could, throw a dart and you'd pretty much get close to the target. And then finally, from the intergalactic medium perspective, if you're trying to match the neutral fraction on the top or the photoionization rate, you can more or less tune the escape fraction of your galaxies in your simulations and reproduce almost all the constraints that we had. And so, like I said, life was good as a theorist because with limited data, you could come up with some really fun theories to test out and you can get pretty close. Of course, as JWST came along, things got a little bit tougher. Nevertheless, I should mention, even with limited data, there were still various high redshift anomalies that we weren't able to match. This first one is a galaxy at redshift 9.1. It's an observation by Takuya Hashimoto. And what you can see is that if you look at these 2 points on the right-hand side, these are your Spitzer bands. And you'll notice that there's a very big break between the point in the red and the point in the blue. And this was interpreted as a Balmer break at redshift 9.1. And Balmer breaks are typically linked to aging stellar populations. In this case, they estimated the population age was 250 million years, which is quite old, even at a redshift of 9.1. If you look at the strength of Balmer breaks of simulations at similar redshifts, this is a work by Christian Pingelli. And it's from the fire simulations, but I would say this is more or less representative of what all simulations are doing. The left-hand side shows the distribution of Balmer break strengths from the simulations, and on the sort of right-hand side yellow region shows the strength of this break, and simulations were really struggling to match the strength of this break at high redshift. Another one that's been talked about a lot from ALMA is the excessive nature of the O3 to carbon-2 ratios. So this is a plot by Yoshihari Kane, where on the x-axis is star formation rate, the y-axis is O3 over C2 luminosity. The red points are your high redshift galaxies. The blue and the green regions represent low redshift dwarf galaxies or starburst galaxies. And if you look at high redshift simulations, you see sort of an opposite trend, whereas you go to high bolometric luminosities or high star formation rates, you're getting lower and lower O3 over C2. And so there is a tension that hasn't yet been solved. Again, this is consistent for most simulations, not just the ones I'm showing. And there might be some new physics like bursty star formation, top heavy initial mass functions, or maybe it's just due to non-solar metal abundance patterns. Another example, which I'd say is still very puzzling today, is the detection of extended carbon-2 halos above redshift 6. So this is the plot by Seiji Fujimoto from 2019, and you can see that the carbon-2 halo they detect goes all the way out to around 10 kiloparsecs. Here's a failure of my own simulations, where if you just look at the blue line, that's the carbon-2 for a stack of galaxies in our simulations, and you can see it well under predicts these black points, which are from Seiji Fujimoto. And it's unclear why the simulations are struggling so much to get the cold gas and the CGM correct at high redshift. It could just be due to resolution, but there could be some missing physics here. And again, it's not just my simulation. I've yet to see one that can match this observation. Finally, another one, which was maybe surprising to some of the observers, perhaps less so to the theorists, was the detection of ordered rotation in high redshift. So here's a carbon-2 velocity channel map, and you can see there's sort of approaching gas on the left-hand side and receding gas on the right-hand side. And what this sort of indicates is that if you believe this observation, is there may be some ordered rotation, some well-designed disks at high redshift. If you look into simulations, this can indeed happen. So here you're looking at V over sigma. And depending on the tracer that you're looking at, whether it's carbon-2 or H alpha at high redshift, they tend to find that sort of the colder gas is forming these nice ordered disks, whereas the star-forming regions probed by H alpha tend to be sort of more tracing the velocity dispersion of the galaxy. Okay, now when we come to JWST, the thing I was most excited about was the revolution in spectroscopy. And here you're looking at the Hubble Grism spectrum of GNZ11, which was the highest redshift spectroscopically confirmed galaxy. And here what you see is that they more or less detect the Lyman break. In this case, they estimated it was at a redshift of around 11.1. And if we look at the same exact spectrum with JWST, you see this, really beautiful spectrum. The redshift is actually closer to, 10.6, 10.7. You see a beautiful Lyman break and all of these emission lines that we can actually, do physics with. And this is really, really exciting when I first saw this spectrum. Okay. And now this is not the only one. We have thousands of spectra at high redshift. It depends what you define at high redshift, but I think it's over 1,000 already at redshift greater than 6. And what this allows us to do is place constraints on the properties of what I would call the normal high-Z galaxy population. And here's just two examples. You can see the dates are 2023. The left is from Alex Cameron, the right is from Ryan Sanders. So this is relatively early still in the JWST life cycle. The left-hand plot is R23 on the x-axis versus O32, which is more or less, an ionization excitation diagram, a little bit of hint of metallicity. Low redshift galaxies, the SDSS galaxies are shown in black, and you can see that the high redshift points are sort of well above, based on, this is exactly what we expected based on redshift 2 observations, which are sort of down here towards the end of the distribution. You can play the same game with the N2 BPT diagram. Again, low redshift SDSS points are down over here. And then you can see the high redshift galaxies are sitting sort of up along this track. Okay, and in general, I think it's fair to say that at high redshift, we tend to find harder radiation fields, higher gas densities, lower metallicities, and higher ionization parameters with respect to the low redshift counterparts. And so as a theorist, extracting physics from these spectra, I'd argue, is a real challenge and a very important challenge. And theoretically, we think we know how to do this. So on the left-hand side is one of the first spectra taken at high redshift with JWST. Again, you see all these beautiful and booming emission lines. If you look at something like H beta, which is sort of a counter of ionizing photons, this is telling you something about the star formation rate on very short timescales. If you compare to Balmer lines like H beta and H gamma, the ratio, which we think we know from case-B recombination, this tells you something about dust. If you look at two different ionization states of the same atom, in this case, it's oxygen 3 versus oxygen 2, you can learn something about the ionization parameter of the galaxy. If you compare metal emission lines, in this case, oxygen, with hydrogen emission lines or Balmer lines, you can learn something about the metallicity. And finally, the overall shape and normalization of the continuum that you're seeing is telling you something about the stellar mass and the star formation history of the galaxy. You can play the same game in absorption as well. On the right-hand side is a beautiful spectra from Muse at redshift 1.3. And if you look at these, really strong absorption features, you can learn a lot about the intervening gas in the CGM. You can learn things about the metallicities of outflows, velocities of outflows, column densities in the simulation, and total mass outflow rates. So I think over the sort of next 5 to 10 years, we're really going to start constraining ISM properties of galaxies at redshifts as high as greater than 10. We've already seen emission lines now up to redshift of 14.4, which came out earlier this week, which is, I thought quite remarkable. And the CGM definitely greater than redshift 5. And I think this is, again, extremely exciting because all this data is useful to constrain in our models of galaxy formation. Okay, so you can ask, how do we actually do this? How do we analyze these spectra? Well, the typical method is to use what's called photoionization models. There's various codes, there's cloudy, there's mappings, etc. And the idea is you take some source and you put it in the center of a gas cloud. In this case, I'm showing you a spherical cloud. You can switch it to a slab. You can change your source from stars to AGNs, but in general, there's a very simple geometry with a source irradiating it, and you run it into equilibrium. And this work, was pioneered back in, the 60s and 70s, but, really came to fruition in sort of the 90s and early 2000s. Here, you're seeing a bunch of low redshift galaxies at black points, and this is the N2 BPT diagram. So N2 over H alpha on the x-axis versus O3 over H beta on the y-axis. And these contours and grid lines are really showing you what happens if you change parameters like metallicity, which goes like this, or ionization parameter, which is sort of walking you down the ladder. And the idea behind this is that you can more or less map out the entire sequence you see at both low and high redshift using these very simplified photoionization models. Okay. Now, I should remind everyone, of course, that a real galaxy, looks like this. It's not a simplified geometry. It's not just a source behind a gas slab or in a spherical H2 region. And I think, given that we've just launched this, $10 billion telescope that's giving us all of these, really amazing emission and absorption features, you can ask, how can we do this better? And more specifically, where can photoionization models go wrong? And how can we actually improve these things? Okay, I'm going to give you 3 examples of where photoionization models tend to perform poorly. The first example is if you just take your standard sort of homogeneous geometry, homogeneous glass cloud, and you just add a little bit of turbulence. Okay, so on the right-hand side, I'm showing you what it looks like. In this case, we've just taken a homogeneous gas sphere and we've just stirred it up with some Mach number and some ratio of compressive to solenoidal turbulence that more or less matches what we think the ISM looks like in the Milky Way. And we put a single source at the center of this turbulent H2 region, and we just run it until it reaches equilibrium. And you see, instead of being a sphere, you get this sort of beautiful butterfly shape. And temperature, you can see that the oxygen 3 is volume filling, and the oxygen 2 forms right at the edge of your ionization front. Okay, and so this has some mean density, and you can ask, how did the emission line ratios change in the turbulent regime compared to the, the same density homogeneous simulation? So on the x-axis, we're varying metallicity. On the y-axis is the ratio of O3 over H beta, N2 over H alpha, and O32. The black points are the result from this sort of homogeneous distribution of gas, and the blue points with error bars are just 10 realizations of the same mean density, but now with turbulence. And what you can see is that in general, O3 over H beta systematically drops, N2 over H alpha systematically increases, and O32 systematically drops as well. And these are, relatively large factors, in some cases factors of 2. And since we're using these strong line diagnostics to infer physics at high redshift, I think it's start time we, include things like turbulence in our photoionization modeling.
And
Another effect.
Is it possible to ask a
Yeah, sure.
clarification very quickly?
Yep.
Why is it that the O3 decreases so much compared to the O2? Or
Yes,
whatever, why
so
is the O2?
it's both. So O3 is going down, and O3 is going up. So we're still working out exactly whether or not this is the case for all turbulence setups, but it seems to be a relatively generic behavior because they also found it, Yifei Jin based at Harvard found the exact same thing. So the O2 tends to be going up for sort of 2 reasons. One, the surface area of this sort of H2 region seems to be increasing, which is giving you more O2. And then the oxygen 3 seems to be going down a little bit in our case, because what tends to happen is we randomly place the source just at the center of the box. And if you stir the medium up, you're volume filled by low density regions. So the density in the oxygen 3 tends to be a little bit lower than the mean. And then of course the oxygen 2, which goes, right at the end, the ionization front is preferentially truncating at the higher density regions. So still a lot to be determined here, but this does seem to be a generic behavior if you just randomly place a source. If you do sort of what we call peak driving, where you place the source in the absolute peak in density, you might get a different result. But it's unclear whether or not the ISM prefers this situation or the other situation. But I'd say if the sources are randomly distributed, this is a generic behavior.
Thank you.
Okay, so the second effect is non-equilibrium. So as I just said, we typically run these photoionization models fully into equilibrium, but it's not clear that's always the case. So this is just a very simple setup where we run a disk and we allow for non-equilibrium evolution in the gas temperature and the electron fraction and the ionization fractions of every species. And what you're looking at is a distribution of density on the x-axis versus temperature on the y-axis, and it's colored by the ratio of the electron fraction in non-equilibrium to the electron fraction in equilibrium. So you see this track here, this is green. This is gas that is over ionized for its given temperature. And this is the well-known effect. It's called a recombination lag. And in this regime, what's happening is that the cooling time of the gas is faster than the recombination timescale, which gives you more electrons at a fixed temperature, okay? You see a little bit of gas in purple here on the left, and this is gas that is under ionized for its temperature. So you're basically heating it faster than it's ionizing. And this effect is a little bit less well studied, but it can occur sort of in 2 ways, at least 2 that we know of, one of which is shocks. And the second one is you can actually heat the electrons directly using cosmic rays without, ionizing the gas in general. And the third effect, which I think is particularly important at high redshift, is the distribution function of H2 region properties can bias measurements. And so what do I mean by this? In our standard sort of photoionization models, we assume sort of a uniform H2 region, either in density. Of course, you can have a temperature gradient, but in this simple example, I'm just showing you a uniform temperature and uniform density. And what I've done is I've just changed the mean temperature of this gas cloud, and I asked, how well can we measure metallicity when I fix the metallicity here when the gas is completely homogeneous? And this is using what's called the direct method, which is widely considered to be the gold standard of metallicity measurements in high redshift. The y-axis is the deviation from the true metallicity. And what you can see is that in this perfectly uniform temperature situation, I perfectly recover the metallicity of this gas cloud. Now I go to the next most obvious setup, which is where I allow the temperature to fluctuate, but again, keep the metallicity fixed and keep the density fixed. And here on the x-axis is again the mean temperature of either a Gaussian distribution in blue or a log normal distribution in orange. And what you can see is that as once temperature fluctuations are present in the system, the metallicity is systematically deviating and it's always low. So anytime there's temperature fluctuations, if you're using this method, you will always underpredict metallicity. And that is a generic behavior and it just comes out of the mathematics. And so this is really important because we don't know a priori what the distribution function of H2 region properties are at high redshift. And when we're using our MSA, it's oftentimes covering a whole galaxy, which likely has many H2 regions. Okay, so how can we improve on this? One idea is to sort of combine these photoionization models with galaxy formation simulations. We've been doing this for many years. On the left-hand side, you're just seeing an example, high redshift galaxy at redshift 10. In this case, it's a disk. And each one of these gas cells has some properties. It has some temperature, some density, some metallicity, some radiation field. And of course, these simulations don't have all of the, really detailed physics that's in these photoionization models. So we can take each individual one of these cells and run them through a photoionization code like Cloudy. That's what we call the black box of post-processing. And if you do this, you can make these, beautiful maps. In this case, they were done for ALMA. You see your carbon 2s, your oxygen 3s, some of your nitrogen emission lines down here. And I would argue that there's a lot we've learned from this, and this has been relatively successful. But there's a huge number of assumptions that go into this black box of post-processing. For example, as we just discussed, the system is in equilibrium. If for people that don't resolve the detailed physics of the ISM, you need to make a guess on what the ionization parameter is. You need to understand the role of the diffuse gas, geometry, et cetera, et cetera. And it's almost impossible to match all of the properties in your simulation with sort of the assumptions that you're making in your photoionization models. And I think this is really problematic because there's, groups that have post-processed the same simulations and come up with, in some cases, up to orders of magnitude differences in emission line luminosities. And so galaxy formation simulations are great, but they're sort of missing all of the detailed physics we need to model the spectra of these galaxies from first principles. And so a couple years ago, I decided we should try to remedy that. And what I wanted to do is I wanted to combine the detailed physics that's in these photoionization models with these 3D galaxy formation simulations. And so we call this code Ramsey's RTZ. And in one sentence, what it is it's non-equilibrium chemistry coupled to on-the-fly radiation transport. And so what we're doing is we've taken all of the primary processes that control ions and molecular gas. So these are things like collisional photocosmic ray ionization, radiative dielectronic industry combination, and charge exchange processes, and have coupled it to on-the-fly radiation hydrodynamics, where the radiation field is allowed to fluctuate. Here's just an example of what that looks like. On the x-axis is time, and in the y-axis is ionization fraction of oxygen over here, nitrogen, carbon, magnesium. We just start everything from neutral and just let it evolve until the system reaches equilibrium. So the dotted lines, the dotted horizontal lines, this is sort of what would come out of a code like Cloudy or mapping as the equilibrium answer. But of course, in our code, we can sort of follow the entire non-equilibrium behavior. And if a galaxy sort of happens to be out of equilibrium, that's going to be well captured by our simulation. Of course, just modeling the ionization states and molecular abundance isn't enough. You need all of the thermochemistry processes that control the gas temperature. These are things like cosmic ray, photoelectric, H2 and dust heating, things like cooling from primordial species, molecular hydrogen, CO, metals, dust recombination, interactions between dust and gas, and then also all of the cooling and heating that come with galaxy formation. So for example, adiabatic expansion, shocks, supernova, turbulence, gravitational compressional heating, et cetera. And this bottom bullet point is really where the 3D numerical simulations are performing well. And of course, we have to calibrate some of these processes. There are some free parameters, and I can tell you how we do this. So on the x-axis of this first plot is density, on the y-axis is temperature. These orange points are sort of the expectation from the local Milky Way ISM. And so these different color lines are different metallicities. If you focus on this bright green one, this is the solar metallicity gas. And you can see it agrees pretty much with all of these other red lines, which have been predictions going back, all the way to the mid-1990s of what the Milky Way's ISM looks like. Of course, not all gas is at solar metallicity. So you can ask, how does this temperature density relation change as a function of metallicity? As you drop to 10% solar, you can see the cooling instability actually happens at lower densities. And then as you go all the way to 10 to the -5 solar, where you're dominated by molecular hydrogen cooling, you see that the temperature is not decreasing as fast due to the sort of much more inefficient cooling. You can play the same game with pressure. You see these beautiful S curves as you go to higher metallicities. This is again indicative of a multi-phase ISM where you have gas at different densities and pressure equilibrium. Of course, as you go to the lowest metallicities in these 1D models, what you find is that the gas in the ISM is actually no longer even multi-phase. And so what we do is we constrain the properties of our cooling and our heating to reproduce the Milky Way's ISM, and then we see how it performs at different metallicities. Okay, and this is a relatively new code. Many of you are probably wondering, can I even trust this? And I think that's a fair question. We've done a lot of calibration tests to make sure, we're producing realistic line luminosities. Here, you're just looking at density on the x-axis versus line luminosity on the y-axis for various lines like oxygen 3, oxygen 2, H alpha, H beta. The dotted points are from our 3D simulations, and the lines are from cloudy. And for the most part, on average, the differences between the emission line luminosities in our simulations are less than 10% when we run them to equilibrium. There's some differences in choices of atomic data, choices of dust depletion. And so we do expect some differences, but overall, you can run these sort of Stromgen spheres with our code and cloudy and get, very, very comparable answers. Okay, now for many of you, I realize this is extremely abstract. And so, what does this actually mean for galaxy formation simulations? So to try to put it a little bit more into perspective, a typical simulation that you run without this type of physics produces things like, the gas density on the left, a stellar distribution, a temperature distribution on the right. And these are what I would call mostly unobservable properties of a galaxy, okay? And if you run a same simulation with Ramsey's RTZ and Prism, we can actually directly predict the observable quantities. And so here you're seeing, we of course get the gas distribution. You have H1 and H2. We get low ionization states, gas and molecules. Here's molecular hydrogen, oxygen 1, carbon 2, CO. We have the radiation field. Here I'm just showing you the far UV all the way up to the helium-2 ionizing bands. You can see it's very different. This all goes down even into the infrared. But if you look at this column on the right, here you see the H alpha, oxygen 2, oxygen 3, and nitrogen 2. We're actually measuring the level populations of the different species in our simulation, which allows us to predict these emission line luminosities directly on the fly without any post-processing. Okay. So what we're doing now is we're pretty confident our code works, is we're trying to run these very detailed high redshift galaxy formation simulations. Our project is called Megatron, and what it is it's an early Milky Way mass galaxy. And so what it is, it's Milky Way mass at redshift 0, but we follow it from very high redshift, from around redshift 150 or so. And it uses all this detailed physics. So it has, very high resolution in dark matter, stars. It includes population 3 stars. The spatial resolution gets down to about 1 parsec when the first population 3 stars form. The IMF is sampled for every star particle. So we get this stochastic chemical enrichment for every element that we track. It includes heaps of physics for supernova, various channels, quark collapse 1A, hypernova, parent stability supernova. It includes stellar winds. And what we've done is the calibration for the feedback was done in the Wintergarten project down all the way at redshift 0. It has 82 species of non-equilibrium chemistry, coupled to 8 bins of radiation transfer. Another thing we do, which I'll show you perhaps a little bit later, is we enhance the resolution in the circumgalactic medium. So for some of the simulations, we refine on the cooling length of the gas, which gives us sort of much more resolution in the lower densities. And we have various runs with different physics, including strong and weak feedback and a changing IMF. And there's 4 science goals of this project. It's to understand star formation at cosmic dawn and how we transition from population 3 to population 2 galaxies. We also want to constrain galaxy formation and the interstellar medium in the epoch of reionization. We're looking at the CGM towards cosmic noon. And because these are Milky Way mass galaxies where we have the dark matter all the way down to redshift 0, we have some projects looking at reionization and near field cosmology. Okay, so here's just a movie of what this large Lagrange region looks like between redshift 5 and 4. You can see the dark matter on the top left, the gas distribution, the stars, the gas temperature, the Lyman-Warner flux, and the ionizing flux. And if you just focus on the bottom right panel, which is the ionizing radiation, you can see as the star formation rate is going up and down in the simulation, this radiation field is pulsing. Sometimes it's escaping and making it out into the circumgalactic and even in the intergalactic medium. Okay. And sort of this is the direct response of this sort of stochastic star formation that's occurring. And of course, many of you have seen simulation movies exactly like this before. There's nothing really particularly new about the simulation movies that I've just showed you. But again, because we're solving for the different non-equilibrium ionization states and then computing the level populations, the emission lines, which are observable, are coming out for free. So you can see H alpha on the top left. You have oxygen 3, 5007, 4363, the O2 doublet, nitrogen 2, and helium 2. And these pulsations you are seeing in the ionizing flux are clearly impacting out here in the circumgalactic medium. You can even see the CGM fluorescing as these, this ionizing fronts pass over the circumgalactic gas. And this is really the novelty of these simulations, is that, we have, hundreds of thousands of spectra coming out. And I'll show you those in just a second. That's more of, what I would consider to be low redshift. Here's a high redshift movie. You're looking at the gas density in purple, the H beta emission in white, and the oxygen 3 emission in 5007 emission in yellow. You see these bubbles forming. This is actually the ionizing photons carving H2 regions into the intergalactic medium. You're literally seeing reionization happen. We start the simulation with 0 metallicity. So of course, all of the yellow that you see was formed by population 3 and then population 2 stars. You can see that oxygen 3 emission is coming from the central regions of the bubble. Part of it is due to the fact that the oxygen hasn't made it out far enough into the intergalactic medium, but part of it is also due to the fact that not every region that emits an H beta is covered by the O3 ionization state. And you see, as we evolve the simulation from around redshift 20 to redshift 10 or so, the gas in the intergalactic medium is getting more and more polluted with metals, and then the volume is completely reionized.
A quick question: what was the scale on that previous image?
I think it's about roughly a co-moving megaparsec.
Okay, thank you.
Roughly. I might plus or minus factor of 2 on that. I can't remember exactly how wide I made the box for this movie. So one of the things we've spent a lot of time on is making sure that with these simulations, we can mock JWST observing modes. So here's a massive galaxy at redshift 4, where, we've done all of the dust radiation transport. So you see these, beautiful dust lanes right in the center. It's right after a merger. So this actually isn't Monte Carlo noise. It's not shot noise from the photons. It's actually individual star particles that have been kicked out of the galaxy. You see numbers of satellites. This one has a beautiful dust lane. This is what the MSA would look like if it was placed over this galaxy. So, this is not the exact resolution of the MSA, but it's, this beautiful Balmer break. It's a post-starburst type galaxy. Here's the inner region of the near spec IFU, and you can see how H alpha looks in the different velocity channels going from receding all the way to approaching. And then the background image is just combining near cam filters, F115, F150 in the blue, etc. So we can pretty much mock near cam and near spec, except the GRISM, pretty well now for every single galaxy in these simulations. Okay. And so our library of spectra, again, there's no post-processing of these really. And so for every single galaxy, we get a full spectrum. There's over 200,000 in our library right now. And one of the things I'm really excited about is we can more or less reproduce the entire spectral diversity seen by JWST from these simulations. So what I've done here is I've taken, these 200,000 spectra just in the UV all the way down to the infrared. We've sampled the spectra at around 10,000 points, and I've just taken these 10,000 points and I've projected them using an algorithm called UMAP to see what they would look like in 2 dimensions. So these UMAP1 and UMAP2 parameters more or less try to take the distance of the spectra in this very high dimensional space and map it so those distances are conserved in the low dimensional space. And what you see is this sort of continuum of spectra here on the left and this offset blue region here on the right. So what I've done is I've just by hand colored these regions, okay? And you can stack the spectra in those different colors. And if you look in this bottom right, you see I have star bursting galaxies moving more along this continuum. Now I see star forming, lower equivalent widths, no Balmer jump. going to this sort of purple region. Here you start seeing a Balmer break appear. These are your aging and post-starburst. Then as you get all the way up to this wing, you see almost no emission lines, very strong Balmer break. This is what we call our mini quenched galaxies. And then finally, this offset region here on the right is our population 3 systems, which is clearly different physics from this continuum here on the left. Okay. And I'm going to show you just sort of a few brief results from Megatron. First thing we've learned is that POP2 star formation dominates extremely quickly, but the population 3 epoch is actually extended to very low redshift. And these dotted lines represent the star formation rate as a function of redshift of population 3 stars in our simulations for different models. And then up here, you see the population 2 in solid lines. And you'll notice that basically after there's a burst of population 3 stars, POP2 immediately dominates, okay? So almost at all redshifts, you're dominated by POP2 star formation. However, we still have low metallicity pockets, even down at redshifts 8.5 or so. One of the things I'd like to point out is if you look at the UV slopes of the population 3 galaxies as a function of redshift, those are shown in magenta versus the population 2 galaxies shown in pink. You'll notice that the population 3 galaxies are even redder than the population 2 systems, which is not what's typically discussed, okay? And this is due to the fact that the nebular gas is outshining the stellar emission in the population 3 systems, but not always the case in the population 2. So if you're looking for POP3 galaxies, you should actually be looking for redder systems at high redshift and not the bluer systems. Extreme emission line galaxies are pretty common at these high redshifts. However, to get the most extreme emission lines, we require really unique star formation histories. So what I've done is I've taken all of the galaxies in our simulation and I've stacked the star formation rate normalized at the present epoch by their H alpha equivalent width. So if you go from yellow, you see these are very sharply rising star formation histories, and black is sort of declining star formation histories at low equivalent widths, okay? And to get a galaxy with an H alpha equivalent width, sort of upwards of 2000 angstroms, what you need is a galaxy that's undergone a star formation rate increase of around a factor of 1,000 over the past 50 million years. And that is a very, very extreme burst of star formation. And this is more or less generic, independent of the physics that we put in. So these extreme emission line galaxies we're seeing at high redshifts are sort of these most catastrophic outliers in their star formation history. Okay. One of the things we're extremely excited about is these optical strong line diagnostics that we're often, using at low redshifts. Here you're looking at, the BPT and VO diagrams. It's N2 over H alpha, S2 over H alpha, and O1 over H alpha versus, O3 over H beta. Each one of these different rows shows you results from simulations with different physics. And what you'll notice is that these diagnostic diagrams are different depending on the subgrid physics that we put in. So historically, we use things like, the luminosity function, the stellar mass halo mass relation to constrain the subgrid physics on our simulation. But here I'm showing you now really for the first time that these strong line diagnostics may even present a tighter constraint on the subgrid physics that we're putting in because these, diagnostics are quite different. And you can see sort of the histograms on the bottom panel to demonstrate that. So now with all this JWST data, I think it's time we start revisiting these subgrid models that we're putting in using these diagnostics as a constraint. One of the things that we're doing that's quite different from many other simulations is we can do these apples to apples comparisons between simulations and observations, okay? And so on the x-axis is stellar mass, and on the y-axis is metallicity, measured in 12 plus log over h. And you're probably thinking, okay, stellar mass is not an observable quantity, and metallicity is also not an observable quantity. So what am I talking about apples to apples? Okay, but of course, when we try to measure this for the metallicity, we use the strong line method, and stellar masses are inferred from things like SED fitting. So what we've done here is we've taken the simulation, then instead of plotting the true stellar mass and the true metallicity, we've processed them exactly like an observer would. So we've inferred the stellar masses using SED fitting, and we've inferred the metallicities using the direct method metallicity. And in general, what you see is if you look at the contours in black versus the different colored points in sort of pink going down to this beige color, that's sort of the difference between the true contour and where our simulation measurements are coming in using the observer methods. And for the most part, for different models, it's pretty good and in pretty good relation with observations in the case of this bursty star formation model. However, in the case of our variable IMF model, you can see that the contour is completely offset from our measurements, again, because these SED fitting codes are assuming some IMF, which is very different. And I think this is really important because when we actually compare simulations and observations, it's extremely important we use these apples to apples comparisons. A final thing that we can do with these simulations is that instead of using SED fitting, what we can do is we can use the simulated galaxies as almost a basis set, and we can take the observed galaxies and find sort of the closest galaxy or the closest combination of galaxies in our simulation to infer their properties. Okay, so this is a very complementary approach to doing types of SED fitting. And this was really pioneered by my student, Nick Chustakov, where what he did is he tried to find the combination of F escape and psi ion, which is the number of leaking ionizing photons that are coming out of real galaxies, in this case from the JADE survey. And he tried to do that by matching them to the spectra of galaxies in our simulation. And what he found is that he gets, very, very reasonable answers, actually relatively consistent with what some people were doing with SED fitting. So I think this is a nice complementary approach moving forward. In the interest of
ask a quick clarification.
Yeah, go ahead.
Where is the F escape coming from with these redshifts? I'm not sure I follow.
Yes.
What's the observable here?
It's not there. The observable here is just the total spectrum of the galaxy. And so what Nick did is he used like simulation based inference. And since in the simulations, we know F escape times psi ion, or for those of you that don't pay attention to these quantities, n dot ion, what he did was that he basically trained the model on the simulated spectra to predict n dot ion. And then he applied that to real spectra. So we don't directly measure F escape or psi ion. What he's using is the simulations essentially as like a template set and trying to predict what this quantity would be. So it's the alternative to SED fitting, which would be doing the same thing.
Right, but my point is the observed data point here are also model dependent because there isn't such a thing as an escape fraction measured at redshift above 5.
No. So that's what I'm saying. These data points here aren't observed. These data points are the predictions from Nick's simulation-based inference model. So the y-axis is taking the observed spectra, running them through the SBI, and predicting F escape times psi ion. So what I'm saying is, of course, you can't measure F escape at high redshift, and of course, you can't measure n dot ion at high redshifts. You, of course, infer it. So you either infer it using SED fitting codes like bagpipes or Beagle, or try to measure psi ion and infer F escape, based on any of these low redshift calibrations. This is a completely different approach where we just take the entire spectrum and then predict n dot ion directly. Okay, so it's a very it doesn't mean it's right. It's just a very complementary approach, and the model has been trained on the simulations, so we know it performs well. So it's an indirect estimate, but it's a complementary approach to what we're currently doing. And the nice thing is it doesn't separate F escape and psi ion, because people tend to multiply mean F escape times mean psi ion, and actually, as you know, you can't do that, right? They tend to anti-correlate with each other.
Okay, thanks.
Yep. In the interest of time, I'm going to skip the circumgalactic medium and near field cosmology. And in the last sort of 5 to 7 minutes, I want to emphasize that this new generation of simulations can match many high redshift properties of early galaxies. But I would argue that we often learn more when things go wrong. And so I really want to highlight what we can't reproduce at the moment with the simulations, because that's where new physics comes in and new constraints come on galaxy formation. And so one of the things we learned really early on about high redshift galaxies is that some of the more compact ones tend to be extremely nitrogen enriched. Here's some work we did with Alex Cameron. So on the x-axis is metallicity measured as 12 plus log over H, and on the y-axis is N over O. The low redshift sequence with sort of a primary plateau and secondary nitrogen production is shown here on the bottom. And our estimates for GNC11 are well up here. And so you can see this is sort of in a completely different ballpark in terms of nitrogen emission. Here you can see these booming nitrogen 4 and nitrogen 3 lines. These have now been seen for many high redshift galaxies. I'll highlight one published recently by Rohan Naidu. This is the redshift 14.4 system. And indeed, you see there seems to be nitrogen 4 excess in this galaxy as well. You can ask what physics drives this excess in nitrogen. It may just be a peculiar star formation history, but this requires fine tuning. And given that we've seen so many of these nitrogen emitters, I think this is unlikely to be a case. We proposed with Alex, it could be things like tidal disruption events where you're just dragging the nitrogen directly out of stars. There's no other obvious signatures of this or any time variability that you may expect for certain TDEs. You can't really rule this out, but I don't think there's any strong evidence for this. You can do it by colliding stars. When you collide two stars, not all of the mass ends up in the final remnant. Some goes into the ISM. The densities at high redshift are known to be very high, where these stellar collisions are likely to occur. But the yields of these collisions are highly uncertain. So it could be this answer, but still TBD. Corinne Charbonneau proposed supermassive stars. This is extremely fun physics. These are stars, of order 10,000 solar masses, maybe even more. This would really be a nice solution, but we've never seen one before. So that would be cool. We can't rule it out, but it's hard to say this is the case. Could be very massive star winds. I'd argue, why don't we see this more often, or what does it imply for the IMF? But this could be very much contributing. It could be Wolf-Rayet stars. There's an analog nitrogen emitter at low redshift, Markarian 996. I should specify that the spectrum does look very different. And it's also not clear how sort of similar Wolf-Rayet stars behave at these very low metallicities. It could be a combination of all of these things, or your other favorite scenario, but there's still a lot of physics we don't know about where this nitrogen emission is coming from. And it's clear that the vast majority of this, besides perhaps the peculiar star formation histories, is occurring in the simulations. One of the things we know about these nitrogen emission galaxies is that they're extremely compact. So this is first pointed out by Yushi Harikane and then sort of updated by Rohan Naidu. So here you're looking at galaxy size versus redshift. The sort of weak nitrogen 4 galaxies seem to follow the sort of 1 plus z to the minus 1.1 relation for size. And the nitrogen emitters are extremely compact and falling down here. Another thing that was pointed out by Peter Senchina is that sort of the nitrogen over oxygen ratios seem to be consistent with some low redshift globular clusters. So many people have proposed that there may be some link between sort of the high redshift nitrogen emitters shown here in red and low redshift globular cluster formation. I would postulate, though, the question, is there actually enough nitrogen? So, for example, a globular cluster at sort of 0.1 solar metallicity that has 10 to the 6 solar masses in stars requires 71 solar masses of nitrogen, and a lot more if it's significantly nitrogen enriched. But if you look at this topping object, which is over here at redshift 6, where we can try to estimate the amount of nitrogen, there's only 6 solar masses that's observed. So we see much less nitrogen than we actually need. Now, you can argue maybe we're just not seeing it all. Maybe some of it is sort of in the neutral phases and we're not probing, or maybe the nitrogen is coming out in bursts. But there seems to be not enough nitrogen right now in order to even produce a globular cluster of this mass. And of course, it's much lower for even more massive globular clusters. I should emphasize that there's some low redshift analogs that we really need to study in more detail. The left-hand plot is showing you the spectra of the Lynx arc at around redshift, between redshift 3 and 4. You see this booming nitrogen 4 emission line. Here's another galaxy that was detected with JWST around a redshift of 3, again, booming nitrogen 4 emission. So these galaxies, we can actually hammer with the IFU, and I highly recommend we do that in the next cycle. If any of you are on the TAC and want to give us time, I would be very grateful. On the right-hand side, this is actually the closest spectra I found to GNZ11. You see this extremely strong nitrogen 4 emission, carbon 4, helium 2, and nitrogen 3. This isn't even a galaxy. This is an individual star in the LMC. And so I think there's actually some really nice parallels by some of these extremely peculiar stars and what's going on at high redshift. And I think all of this needs to be studied, particularly in the UV and optical, where all of this physics is happening. I should emphasize again that the peculiar abundance patterns can impact physics. So I think this is a really nice result by Yanagisawa et al., where if you look at the helium over hydrogen versus the nitrogen over oxygen, you see this strong trend that the galaxies that are highly enriched in nitrogen also have enhancements in their helium. This is not surprising. This is expected just, from stellar evolution. However, I should point out that if you actually increase the helium abundance and the mean molecular weight of the gas in the stars themselves get brighter, okay? And so here you're looking at the bolometric luminosity normalized by the bolometric luminosity of the same star at primordial abundances. And as we increase the helium abundance in the stars are getting brighter, okay? So if you just focus on these lines, which are the meso models at different metallicity, if I plot GHG2 and GNZ11 over here, you can see that the stars in these galaxies, the ones that are enriched, should be about 50% brighter than a typical star using primordial abundance patterns. Another thing that we're often seeing is that the nebular continuum is often extremely strong at high redshift. Here's a stack I made for galaxies above redshift 3, and you see this booming Balmer jump, which is indicative of gas emission. And this is not surprising. Again, if you change the star formation histories, on the right-hand side are just 3 different models of a smoothly rising star formation history, a cyclic star formation history, and an extremely bursting star formation history. On the left-hand side, you're seeing the spectrum. The purple represents the nebular continuum, and you see as you go from sort of a smooth star formation history to a bursting star formation history, this Balmer jump feature in the nebular continuum starts rising over the stellar emission shown here in blue. Okay, so we do expect that if high redshift galaxies are bursting, we are going to see these Balmer jumps at high redshift. Okay, and so, however, for some galaxies at high redshift, it may be the case that the nebular continuum is outshining the stellar continuum at all wavelengths. And so here's 3 examples where, again, you see this Balmer jump feature where the continuum on the blue side is higher than the continuum on the red side. You see that the UV slope is extremely flat. These galaxies have a beta of around -2, -2.1. You see a very strong UV downturn here, which is often interpreted as a damped Lyman alpha system. However, I debate that a little bit because you see extremely strong Lyman alpha in these galaxies, indicative of a Lyman alpha escape fraction of around 30%. And finally, the Balmer decrement indicates that there's no dust in these galaxies. So these flat UV slopes that we see are probably not due to dust. Okay. And you can ask, how can this occur? How can we get the nebular emission so strong in these galaxies? One of the things you can do is you can increase the surface temperature of your star. So on the top panel, what I'm showing you here is spectra of galaxies where I've just changed the stellar temperature going from a typical O star in blue on the left, so something closer to a hot population 3 star here on the right. And you can see that there's sort of no indication of this UV downturn in Lyman alpha for a typical O star. But as you go to these very hot massive stars, you see that this UV downturn in Lyman alpha again starts to appear. And this would seem to imply that for these galaxies I just showed you, there would be a hot massive stars present and potentially even a top heavy ion. There's a number of other scenarios. I don't really have time to discuss them, but I'd argue that all of them have, fine tuning required. So please ask me, after this if you want any questions about those. And
sorry, very quickly. Would you say that the shape around the Lyman alpha is the 2-photon continuum then?
Yeah, it's basically identical in all of the galaxies.
Right.
And so the question is how do you get a DLA column of 10 to the 23, which is what's required to explain
I don't
the shape?
think I don't think that's that, but it's probably 2-photon continuum. That's what you're suggesting.
That's exactly what I'm arguing for, that this is 2-photon emission. Yeah. And we have, this is actually outdated. We have another 3 of these. So the final point I want to touch on is one of the biggest surprises that no simulation has ever reproduced is little red dots. These were sort of first highlighted by York Mate. You can see very compact morphology, really, really red in the imaging. And they're sort of categorized by having these V-shaped spectra when you plot them sort of like this in F lambda, where you see it's sort of punching up on the right-hand side and rising towards the red and also rising towards the blue. Okay, and I think it's interesting that the V shape consistently occurs at the Balmer break. So this is really a nice result from David Seton, where he stacked a number of LRDs, and you can see that the V is pretty much occurring at what we call H infinity, which is sort of right at the end of this Balmer series. And it was also pointed out by a number of authors, and York Mate, that many of the H alpha lines, you can see this Balmer absorption feature. Okay, and there may be a connection between this Balmer absorption here in the H alpha and this Balmer break that we're seeing here in the continuum of the spectra. And so the sort of most egregious examples of this are sort of what Rohan calls the black hole star and what Anna de Graaf calls the cliff. Here you're looking at these sort of very, very extreme Balmer break objects. This one's sort of at redshift around 3 to 4, and this one's around redshift closer to 8. And if you just compare the Balmer break strength in these 2 objects to sort of similarly redshift galaxies that are either massive quiescent galaxies or blue or little red dots in red, and then sort of normal typical stellar population in gray, the Balmer break strength are again in just a completely different ballpark. Okay, so it's unclear exactly what's causing this, but sort of the best model that we have that was also pointed out by Kohen Aoshi and the Cambridge group is that if you put a sort of dense gas atmosphere with relatively high density and high column density, you can more or less reproduce this Balmer break and almost completely the shape of this continuum. So because this thing almost looks like an atmosphere and it has a very, very high covering fraction, we sort of described it to be almost like a black hole star. Okay, and this is my last slide. There's a number of open questions in my mind about early galaxy formation. There's still a lot to determine about the physical properties of massive stars at low metallicity in the early universe. This is, in my opinion, one of the most exciting questions. How does stellar feedback and low metallicity regulate the growth of galaxies or not at high redshift? How do Lyman continuum photons escape early galaxies and reionize the universe? What is the physics that's driving these peculiar chemical abundance patterns that we're seeing? How are these black holes and these little red dots are seeded and how do they grow? And I didn't really touch on the CGM, but how are the properties of the ISM and CGM evolving over time? And I really want to emphasize that the UV is one of the best places to explore this physics. A lot of this physics happens sort of between 12, 16 angstroms and around 2000 angstroms. And habitable worlds is going to be like fantastic for something like that, both for low redshift analogs and potentially looking at even higher redshift, particularly in the context of the CGM as well. And so hopefully once it's finally, completed in its design, we'll be able to know exactly more of what we can do with it. But for me, I think this would be really exciting for the type of physics I'm interested over the next, 15 to 20 years. So thank you very much.
Very nice. Wow, that was a speed run through a lot. Wonderful. Okay, so I want to open the floor to questions. We have about 5 minutes, so if everybody can jump in quickly. I have a few myself, but I'd like to give it to the room first.
Een wandelspace maken.
Anyone?
Sorry?
All right, I'll jump in first. So I really like the U mapping of the Megatron. That's a sentence I wouldn't have said a few years ago, but but I like the fact that you sort of could take to see where your spectrum sort of lives in this multidimensional space. I'm assuming that you've used the spectra as the input for the UMAP, or just the emission lines. Okay, so
Yeah.
I was curious if you can then match, for example, SDSS spectra and see where they lie, right? So you can take an observed spectrum and see where they lie in this whole place. I was wondering if you had looked at green peas, because these are supposed to be these era of reionization equivalents, and then we go look at their UV spectra to see their escape fractions, etc. So you have a model for the actual conditions, and I'm never quite convinced that the green peas are actually a good analog for the high redshift ones, right? And having a space like this, you can say like, yeah, the green peas lie here, the high redshift ones lie here, for example. Have you looked at like the equivalency, the how good are the analogs, for example?
Yeah, that's a great question. So I'm going to give you a non-answer and then a slightly better answer. So the non-answer is no, we haven't done that yet. It's been on my mind, not necessarily for the green peas, but I'm happy to do that as well. But to do it more for the high redshift galaxies, one of the things we need to do before we do that is we need to sort of, for every galaxy, we need to take our spectra and map it onto the same wavelength grid with the same line spread function and the same level of noise. So that we can do sort of a more one-to-one comparison. There's nothing preventing us from doing that. Just we haven't done it yet. And then we would play the same game with the green peas. For the answer though, sort of unrelated, when the first JWST spectra came out, the sort of 3 redshift 7 and above SMAX galaxies, we played the game of running what's called an isolation forest, where we took the low redshift analogs, like the green peas, the blueberries, etc., and we asked, how well do these high redshift spectra fit into the low redshift galaxy population? And we found one of them was like perfectly consistent, but then 2 of them were like strongly outliers, like based on these machine learning models. And so it requires some interpretation. And I think there's a lot of parallels between the green peas and the low redshift analogs and the high redshift galaxies. But of course, I think it's unreasonable to think that they're exactly one-to-one comparisons, and the machine learning models sometimes pick out on these small features.
Any other questions? Please. Yes, Claudia has a question.
If no one else, because I have already asked many questions, so.
Go for it.
Okay. Another indication, I'm very intrigued by your explanation of the red dots about Balmer self-absorption. We recently argued a similar phenomenon to explain the observed ratio of Balmer lines, which seem to be inconsistent in some galaxies with case B recombination theory. And one explanation that we give is one possibility is exactly this, that there is self-absorption in the Balmer line, which is interesting because then you have to think about what is causing this large population of excited H1 in these galaxies. So what do you think is causing this large population of excited hydrogen?
That's a good question. In the normal star-forming galaxies, I have no idea because, I mean, it's not a stable state, right? Like you need to trap the Lyman alpha or something like that in order to continually populate it. So for a normal star-forming galaxy, I don't have a good answer for you. I think for these black holes, it's not. I mean, the densities that we're talking about are not unreasonable, and so we've seen conditions like this around. Like we do see Balmer absorption around black holes at low redshift. It's not very common, but it's been seen before. And so I think in the case of the black holes, I'm not super concerned that the physics is like wildly different from these sort of few ones at low redshift that have it. The star-forming galaxies, I have no idea because in theory, the Lyman alpha should be escaping if it's turbulent. And so if it's not, then I'm not sure what's keeping it at that state.
My personal feeling is that these are exceptional galaxies. In fact, these are not the classic star-forming galaxies. So these may be objects that they are very compact, and in fact, they typically have very high ionization state. So they may be very hot stars and very compact. They kind of perhaps mimic a black hole or a small black hole.
Possibly. I mean, one thing we could look at is, I mean, if these galaxies all have density indicators, we can see how high they go. But yeah, that would require, again, really beautiful UV spectroscopy, which we don't have for all of these systems.
These are low redshift, where some of them, but these can be seen. Anyway, that's a very interesting thing, in my opinion.
That's excellent. Sorry, taking notes at the same time. So anybody else have a question? Swara.
So, I mean, really fantastic to see these emission line, maps and the simulations. And I had a question about the measurements that we mostly do for these very compact systems. Those are integrated measurements, right? And you're able to get the full spatially resolved maps of these things. And has anybody from your group or anyone done an exercise of just comparing how the derived properties change, whether you look at, integrated measurements versus spatially resolved map information?
Are you referring like more towards like if we do like pixel by pixel SED fitting versus like the global SED fitting? Or are you thinking more like how are the emission lines changing as a function of sort of distance in the property?
Yeah. So how biased are we when we kind of just talk about integrated measurements and just put them in the BPT diagram?
Yeah, I mean, I don't think I have the plot here. If you take every single pixel, so okay, there's like two things to consider here. The like the BPT sometimes like doesn't even make sense if you're at high enough resolution, because if you're at high enough temperatures where the recombination rate of hydrogen is really low, but you're still collisionally exciting oxygen 3, you get these like absurd O3 over H beta ratios. And so what we find is that if you go to like small enough scales, you can basically map out the entire BPT diagram. And so I think the perhaps the question is how much does an integrated measurement bias our view of the galaxy? I think for something like the BPT diagram, I'm not sure how much it does. I mean, you're always biased to the brightest H2 regions. If there's multiple H2 regions, you're biased towards the hottest, brightest ones on the BPT. That's inevitable. Uh, but I think if you're talking about stellar masses, there's no outshining problem where that can be, that can be a really big problem. And for metallicities, it's a massive problem. Because if you're biased towards the hottest H2 region, that tends to be the lowest metallicity gas, and then
Mhm.
you're biasing your metallicity low. So I think it depends on the exact measurement you're trying to make. Uh, but I don't think for things like the BPT, it's going to massively bias yours, what you think.
Okay. Thank you.
Okay, I think we're over the hour, and that means all of us have to run to the other meeting that started 5 minutes ago. So I would like to thank Professor Katz again. Thank you so much for a really cool talk. Thank you for the slides and the discussion. So thank you all so much for coming. We will see you soon. We'll have a new one. And if you know somebody who you think would make a great talk at the Galaxies SIG talk series, please shoot either me or Aaron an email. Nominate yourself. So these go on to YouTube. They're a great resource to then point to. So please let us know. All right. Happy to see you all next time. Cheers.
Thanks. Bye.